Okay, so we are getting into electric circuits. I've talked about electric current, and now we want to talk about resistance and other stuff. So in the previous video, I kind of got to this definition of the electric current. It says that the electric current in a material depends on several things. First of all, it depends on the value of the electric field inside that material. The electric field causes charges to accelerate, they collide and stop, they accelerate, it gives them an average velocity. Now, the amount of average velocity, which was called the drift velocity, depends on the value of the charge, the number of charges per cubic meter, the cross-sectional area of the wire, and this is U, the charge mobility. Okay, so that's what we have. Now, suppose I have a very simple circuit. So here I have a battery, and a battery has a electric potential across the ends of it. This is the positive side, and this is the minus side. So from here to there is a change of potential we call the electromotive force, partially for historical reasons, but partially because something goes on in here to make this side positive and that side negative, and we'll talk about it later. But that's the electromotive force. And then I hook this wire up from one end of the battery to the other, and it's a really thick wire, has a length L and a cross-sectional area of A. Now, suppose I start right here and I go all the way around and back to there, and I want to find the total change of potential. It has to be zero. It has to be zero because the way that we got this electric potential is from electric potential energy. And the important thing was that the work done by the electric field, the electric force, did not depend on the path. And that's how we were able to do this. So if I start here and go all the way around and get back to where I was, that should be the same as starting there and ending there and not going anywhere. So it has to be zero work done. Therefore, it has to be a change in potential of zero for the whole loop. And this is true for conservative fields, which electric field is. Okay, so now if I break that down, I have, I could say going from here to there, I have a change in potential of EMF, whatever that is. And then from here over there, I have minus V wire equals zero. So I could write the change in potential, I guess it's really a change, across the wire is equal to the magnitude of the potential. Let's say this is a 1.5 volt battery if you want. Now, what causes this change in potential in the wire? Well, there's an electric field that follows the wire inside the wire. This is an electric field, and this is what makes the electrons in there move and at some average velocity. So if I want, I could write EMF equals delta V wire. I should write delta. Delta. It's still a change. And that's for the wire. And that's going to be negative E times L. If the electric field's constant in here, then I can calculate the change of potential as just E times L. Remember that delta V is negative E dot delta R equals negative E delta R cosine theta. So if E is in the same direction as the displacement, then theta is zero, and if it's constant, I can just write this as E times L. So here I have the electric potential across this wire depends on the value of the electric field and the length of the wire. Now let's take this up here and solve this for the electric field. So if I solve this for E, I get I over Q in a U. And if I plug that in up here, I get, I'll write it over here, delta V wire equals, let's just look at the magnitude for right now, so don't worry about the sign. I get I, L, I'm making sure I don't make a mistake, Q in a U. So if this is a one wire, then all of these properties right here, L, the Q, the N, the A, and the U, don't really change. They're properties of that particular wire. So I can actually set all of that stuff. Actually, I'm going to change this. All of this stuff is constant. And I'm going to call that the resistance. And this is going to be L over, now, Q, N, and U depend on the actual type, the properties of the material, and I'm going to call that sigma, the conductivity. So sigma, right over here, R is the resistance in units of ohms. Sigma is the conductivity, and this will have units of 1 over ohm meters, and then length is in meters and area is in meters squared. So that is the resistance, and from that I get this: delta V wire equals IR, and that's how we define resistance. It's that property right there. Now, be careful. Resistance essentially tells you how the relationship between the current and the electric field, essentially. Okay. But this, don't think that a particular wire has a particular resistance. Most wires will change resistance as they change temperature, so this is not necessarily a constant thing. Another thing here is a lot of times instead of the conductivity, we'll use rho, the resistivity, where the resistance is now the resistivity times length over area. But both of these say the same thing. They say that if you have a longer wire of the same material, you're going to increase the resistance. If you have a wider wire, if it's thicker, it's going to have a decreased resistance. So short, thick wires have low resistance. Long, skinny wires have very high resistance. But this is resistance. And with this property right here, we can start doing some serious stuff with electric circuits. But I'll stop right there, and we'll pick up in the next video.